Today's session is part of our theme called Artificial Intelligence, Real Ethical Quandaries, where we dig into the ethics behind how we're using artificial intelligence in today's world. And we're going to be joined by an assistant professor and Triple Duke alumnus, Dr. David Carlson. Professor Carlson's research interests include machine learning, predictive modeling, health data science, and statistical neuroscience. And in this session, he's going to share more with us about AI and the black box. What is it? What do we know? What do we don't know? And how can we trust this black box? So welcome to the Forever Learning Institute, David.
Thank you so much for the introduction. Great. So I'm going to be talking today about opening the black box and what really is explainable artificial intelligence. And so I wanted to start out by really just making a few claims. So I'm going to start out with the claim that machine learning is ubiquitous. Now, one of the first questions we often get is just, what is the relationship between machine learning and artificial intelligence? So I'm going to start out by just saying machine learning is a statistics-heavy subfield of artificial intelligence. So in today, when you hear the term AI, most of our AI or artificial intelligence algorithms are actually working based on this technology called machine learning, right? And AI-powered algorithms are present in nearly all aspects of our lives. It's a shocking amount that it's actually present in everyday thing that we do today, right? I have a cell phone. Pretty much every app on a cell phone is somehow powered by machine learning. Our ability to take photos, our calls, our ability to manage network traffic, our spam filters on our email. Everything we do is basically impacted by these AI-powered algorithms. If you ever get on social media, it's all algorithms all the time, which is, I think, pretty apparent from the news recently. But I'm going to make one more claim here that's going to be a little bit surprising, which is that we rarely understand why modern AI systems make decisions. Right? This is pretty surprising to a lot of people because these systems are everywhere. Right, so surely we must know exactly what they're doing and why they're working the way they're working, and we don't really, right? These are actually still open theoretical questions. So kind of to explain this kind of surprising claim, I'm going to give you about a 5-minute introduction to machine learning. So for those of you that already know it, please bear with me, and we'll get back into kind of exactly what do we mean by explainable AI. So I kind of wanted to just start out by looking at an example machine learning system and explaining why this matters so much. This is a really famous example of machine learning that was done a decade ago now. I really like this problem. The problem is basically, can we look at an image and can we have an algorithm or a computer automatically recognize what's in an image? Right, so the idea is we take a picture like this and we don't tell it what's in it. This was somebody has actually said, well, this is a picture of a mite. This right here is a picture of a container ship. This is a picture of a motor scooter. And instead of having a human tell us this, we're going to have a computer do this. This was considered an extremely challenging problem a decade ago. A decade ago, we thought we were a long way away from actually solving this at all. But these modern deep learning approaches actually came to kind of tackle these problems and actually provide workable solutions. So what happened was there was this algorithm that came out and it started saying, well, we can look at this picture and we're going to be able to, from this algorithm, feed this picture into this algorithm, and it's going to tell us, well, we think we're looking at a mite. We think we're looking at a container ship. If we're not looking at a container ship, we're looking at a lifeboat. We think we're looking at a motor scooter. If not a motor scooter, a go-kart, moped. You can go through, and it started working really, really well. And for those of you that are older than our current teenagers, you can remember a time when we didn't have things like really good working image search, right? This was actually a really challenging problem that's really been developed over the past decade. And it's super relevant, not just for image search, but also things like automatic tumor recognition in the hospital and a lot of different other applications, just even things like sorting photos. So modern deep learning solutions made these systems work. And to explain kind of the problem of explaining how these solutions work, I'm going to briefly introduce what's happening. So when we actually develop a machine learning system, what we say is we're going to have some system, and I'm going to represent it here as a black box. And what happens with a machine learning system is it starts out with no information. We actually give it a bunch of mathematical definitions, and there's a bunch of settings. And when we start out, we say, you know nothing, absolutely nothing. And we make all these settings, we start them randomly, right? And so we get this input here. And because it's a completely random system, we need to be able to learn how to make these predictions. So when it starts out, we're going to start out with really bad predictions. And what's going to happen is, well, let's just go through. Here's a picture of a mite, but our system's completely random right now because it just started. It doesn't know anything. It's like a baby. And it's going to predict that's a leopard. And now, if you look at that, that's clearly wrong, right? This is not actually a leopard. And so what we're going to do is we're going to say, hey, okay, you got that wrong. The true answer here is a mite, right? So we're going to actually look at this and we're going to say, this is a mite. We want you to say that this is a mite next time. So we're going to take this information and pass it back to our machine learning system and say, we're going to change a lot of the little internal settings in this machine learning system to next time we see an image that looks like this, it's going to be a little bit more likely to say mite. And we're going to just do this over and over. So the big key idea of a machine learning system is we can take this and we can repeat this millions of times, and eventually it becomes better and better. So for example, the next time we do it, maybe we get a jaguar, it goes to our machine learning system. Sorry, this is a leopard, and it gets it a lot closer because it predicts a jaguar. It figured out it was a cat, but the truth is a leopard. We just keep doing this over and over and over and over and over again. We repeat this millions of times. We give it millions of example images, perhaps even billions of example images, and we keep training it and we keep telling it when it gets it wrong, how it should change its settings just a little bit to predict better the next time. So this seems like a very kind of drastic oversimplification of machine learning. And I will say that this is a simplification. This is actually not too much of one. This is really how these systems are actually working. Now, the problem is, well, if this was what's happening, why do we not know exactly what's going on? Well, these systems are extraordinarily complex. So if we actually take a peek into what's actually being defined in this black box, what we actually do is we can propagate it out. This is what I'm visualizing here is something called a residual network or ResNet. This is a deep neural network. So this is a shorthand for what's going on. And we have all these arrows connecting what looks to be a graph, right? So this is taking our image as an input, it gets passed here. The information gets processed in some way, gets passed again. There starts going off in all these different directions. And in this network, which is actually not even that complicated by modern standards, there are 21.2 million different parameters or settings. So when you're starting to look at this and saying, well, each time we look at a new image, we're slightly changing 21.2 million different numbers, you start to figure out, well, this becomes a very challenging problem. And so if we have the question then, which part of the system is responsible for the decision? Well, there's 21.2 million different parameters. So what is actually making the decisions here, right? When we make these predictions on data, how is it actually doing that? And why is it doing that, right? So we can go through the mathematical steps by mathematical steps, and it's just getting to such a complexity that it's hard to figure out exactly what is happening to the data. So there's this follow-up question that I'm going to try to address a little bit, which is, does this really matter, right? If we know these systems are working really well, if you have a great spam filter, you may not care how it works. You just care that it does work. And so I want to explain a little bit about why this is something that we think a lot about as a field and a lot as society. So one of the things that I think I at least believed as an undergrad, which is that we used to believe that algorithms are unbiased and fair. An algorithm, if you have it, once it's defined, it does the same exact thing every single time. It can actually understand this is what you do. You take an input, you get an output. It's highly consistent. So you look at this and you're saying, well, it's highly consistent. It's very well defined. That means it's unbiased and fair. And I also used to believe that data is objective, right? You think about data, you collect it from a scientific experiment, and you think that this data is really, really objective. And so what's the problem with training on data, right? So if we train on data, this data doesn't seem like it's got all these like things going on, and it's producing a reproducible algorithm. Well, as I think the field has come to discover over the past decade, this is actually a really big problem because data is biased, right? And so when you might be able to think about, hey, this is the data my company collected or anything like that, or this is the data from a scientific experiment, I don't see how this is biased. And we can get into a lot of the details of what biases may or may not exist in a lot of scientific experiments. But when we start to talk about things like the internet, I think people are going to start agreeing that data is biased. If we're training a natural language processing system, so something that we may want to have generate text or actually read and make sense of text of what somebody's typing in, we might say, pull a ton of examples off of Twitter. I don't know how much people go to social media and look at what people write. There are a lot of problems there, right? And so you see this over and over. So you don't even have to do a very big dive onto news articles to actually understand what's going on, right? If you're using internet data, you pull in a lot of their biases that you get from the historical data. So this is an example that is now getting pretty old, that happened about 5 years ago. Microsoft, it's actually Microsoft Research, they put up a bot onto Twitter. And the idea was this bot is going to just learn. It's an example of how we can learn from society. And what it did was it said, hey, you can talk to me. And if you talk to me, I'm going to learn how to speak language and how to communicate people by having all the users of Twitter talk to me. And within literally a few hours, it started saying incredibly racist and sexist things and was immediately pulled by the company, right? But the real problem was that it was actually just trained off of what people were saying on Twitter, right? And that's really the problem, was that we were using internet data and this data was hugely problematic. We also inherit a lot of historical biases. There was another incident a few years ago where Amazon actually let the community know that they had developed a tool to help screen resumes. And so they were trying to predict who they should hire for technical jobs. And what they found very closely was that if you took the same CV, fed it into the algorithm with a male name or a female name, it would think that you should hire the person with a male name. And that seemed like a very small change and a very worrisome change, right? But this was the big idea where when we're just training off these historical biases, what the system had learned is that, well, in the past, we're largely only hiring men for technical jobs. So in the future, we should only hire men for technical jobs because we're training on the historical data. If there are biases in the historical data, we're going to have those same biases in the future if we're using the algorithm. Now, Amazon got a lot of flack for this, and I will say my opinion of this is I'm actually happy that they put this out in the public domain. They claim they didn't use it. Whether they did or not is a little bit debatable, but I think this is a very important message to the community that when we're training off this data, it really matters what data we use as our input, because if you put garbage in, you get garbage out, but if you put sexism in, you get sexism out. And so this is a problem. And in fact, there's a lot of companies today that are developing AI tools to help screen resumes, and they're getting a lot of these same accusations thrown at them. And because all these data and all these algorithms are proprietary, it's actually pretty hard to know what's going on. One of the most famous examples is how black box AI is being used in high stakes scenarios. So this has been something that has been talked about a lot, where there's software that's actually used to predict whether you're going to commit a crime again in the future. So this is called recidivism, and it's being used to help make things like parole decisions and also how long a sentence should be. There was a ProPublica article a few years ago that claimed that the system that was trained off of a lot of this historical data was very biased against Blacks. Now, I should say, just to be really clear here, that there's a lot of debate about the system. Some people claim it is, some people claim it isn't. It's hard to actually know exactly because you don't exactly know what this company is doing and how they're using data and what exactly their algorithm is doing. And so a lot of these are really big challenges, and you don't actually have to read the news very much to see more and more challenges coming out, right? There's been a lot of talk about Facebook in the recent few weeks because of the complexity of their algorithms and having difficulty understanding what they're actually doing and how they're actually impacting people. And so one of the solutions that's being talked about a lot in academia is, well, can we actually make an AI system explain itself? Can we take a lot of these AI systems that we don't know exactly why they're making their decisions and make them try to explain what's going on? This is the key idea of explainable artificial intelligence. And the argument is, well, if we can make a system explain itself, we're going to be able to start having the debate about whether it's making decisions how we want them to be made. So there's a lot of different approaches to explainability. So for example, one thing you can do is you can limit the information a machine learning system can use, right? So if you want to say, well, we shouldn't make decisions based off age, you don't give it age as an input. If you don't want it being made off of what people have said in the past on Twitter, you don't give it that, right? So you can heavily limit the information that's going into it to say, hey, if we want to make a decision about heart disease risk, maybe let's just give it blood pressure and kind of smoking status. And then if that's the only information it can use, we know that that's the only information going on. We can also use something called logic approaches, which is an alternative to these deep learning methods. And I'm going to give you an example of that in just a second. We can create simpler methods to approximate deep methods, which I'll talk about in a little bit. And we can also construct a lot of bespoke methods for custom situations. So I wanted to talk a little bit about a logic modeling approach. Well, there are some applications where these really complex deep networks are state of the art and by a wide margin. And a lot of other applications, they're not. And a lot of simpler machine learning algorithms can actually work just as well. So this is an example from my really fantastic colleague, Cynthia Rudin, who I think, if anyone's following the Duke News, just won the Squirrel AI Prize, which is a really big prize for AI having a positive impact on society. But I wanted to explain this system a little bit. So this is something called a logic model. And what it is, it's going to predict the risk of recidivism. So if we look at this here, we can say, well, we're going to have a really simple scoring system. And over here, we have points. And what's going to happen is we're going to predict the risk that someone's going to commit a crime in the future if we let them out of prison. And we're going to say the risk is, if your score is -1, is about 12%. If your score is 4, it's about 95%. And so if we have the system here, we can just go through it and we can say, well, if you've been arrested more than twice in the past, you get 1 point. If you get arrested more than 5 times in the past, you get another point. If you have an arrest for a local ordinance, you get another point. If you're young, you're much more likely to commit crimes again in the future, you get another point. And if you are much older at the time of release, you get -1 point. But you can actually go through and on an individual, you can say, well, let's just calculate all these things. And then we're going to be able to get your points and we're going to be able to predict your risk of recidivism. Now, when you're looking at this, I just explained this entire system to you. Now, you might say, well, this is something that someone could write down, and someone probably could write this down. But what this actually is from, this is a different type of a machine learning system that was literally trained in order to try to find a very, very simple and effective rule metric. So it's this idea that if we have all this complicated data, maybe we can find a set of simple rules that actually does a very good job predicting, right? And this is actually does a remarkably good job predicting. This is an AI algorithm, and I think everyone in this audience can probably explain exactly how this AI algorithm is making its decisions, right? Because this is actually a really nice, simple system. And so there's a lot of interest in these logic approaches, which can work in a lot of different algorithms. But one of the places they don't work is in these really complex scenarios where we have natural language processing or we're looking at entire images. It's hard to make a similar system for an image because we don't know exactly what we're talking about. So one of the things that I wanted to get into a little bit was explaining deep networks by similarity. So before I talk about this picture here, I wanted to just say that this is an example of case-based reasoning. To explain what this is, you imagine that you're going to the doctor. So you walk into the doctor's office and you explain your symptoms and they say, this sounds like the last few patients that came in. You're very similar in your symptoms to these last few patients. They all had the flu. I'm going to think that you have the flu too, because you're very similar to these patients that just came in. And this is the entire idea of case-based reasoning. You try to find examples of data in the past that are very similar to the example of data that you're seeing now. And that's how you make your decision. You're just saying, what are you similar to what's happened in the past? Now, what's a little bit less obvious in this scenario, when you just think about it conceptually, is that the doctor is actually using an awful lot of experience in order to figure out how to match patients. We don't use every single piece of information that we know about an individual in order to decide if you're similar, right? When in a doctor's clinic, it doesn't matter how tall you are. It doesn't matter what your hair color is. These are all personal descriptors. But what really matters are, what are your symptoms? Are you coughing? What was your temperature? Are you sleeping well? Are you, do you have a runny nose? Do you have a difficult cough, productive cough? They know what symptoms are actually relevant. And this actually matters when you start trying to adapt these kind of case-based systems to data, because what you need to do is not just say, well, what is similar to what's happened in the past, but actually, well, what in this image, for example, is similar to images that's happened in the past? So this is a system that was actually built to explain deep networks by similarity. So it said, we want to be able to look at an image, and I want that really complicated 31 or 21 million parameter deep neural network to force itself to explain how it's making its decisions. So what it is it says, well, you're going to take an image, and the way that you have to make your decision is you're going to take part of this image that you're seeing, and you're going to show me an image that you've seen before, and you're going to tell me what part you're actually looking at. So if we take this red box here, it's the head of the bird, and you look at this head of the bird here, and I'm not going to explain it, but too much beyond that, but this is just saying, hey, look, this head of this bird is very similar to this head of this bird. This is how we're making this decision. The throat of this bird is very similar to the throat of this bird. The wing of this bird is very similar to this wing of this bird we've seen before. The feet of this bird are very similar to this feet of this bird that we've seen before. So this is the idea. We can actually break down images and say, well, we're going to say that this is a particular type of bird. There's actually lots of birds in this data set. And the way we're going to say whether this bird is of a particular class is by saying, well, can we find examples where it looks very similar to what's happened in the past? And this is one way people go about trying to build up similar explainability in these really deep neural networks. We didn't force it to explain what each individual 21 million parameters are doing. We forced it to explain a little bit about what's just going on in this system. And so one of the other things that I really want to make a point on is that explainability depends on context, right? So explainability doesn't mean that everyone in the world can understand what's going on. This is an example from my own research group. This is something called an electrical connectome. We actually use this to try to understand neuropsychiatric disorders. This is actually a network related to social processing. So if we were to stimulate this network, we can increase or decrease how social a mouse is, which is a really interesting method in neurostimulation. So we can actually stimulate the brain to make this happen. But I'm going to claim very proudly that this is explainable, but unless you have the relevant background knowledge in this area, it's very difficult to explain. And so when I give research talks, I talk for nearly an hour to explain what this is. So this is really the point, though, that explainability is really highly dependent on the situation. What do you need in the situation? What else is going on? So I do want to mention one other alternative approach, which is rather than trying to force an algorithm to explain itself, if we really care about making a fair and just society, another thing we could do is we could actually try to force these machine learning algorithms to be fair. So for example, what we could do is we could say, well, we want to treat sensitive groups the same. We want to make sure that we're treating males and females in a very similar manner. So if we're making predictions on them, we make the predictions very similar across these groups. And this is a really interesting approach that some people are pushing for, but you run into this challenge that it's really still difficult to understand how the machine learning algorithm is making its decision. And you can come up with mathematical metrics of fairness. Now, one of the things that I think may be popping into people's mind when I'm saying mathematical definition of fairness, you might be thinking, how? What is a mathematical definition of fairness? And it's hard. People can't agree on a mathematical definition of fairness, right? And there's a big difference between being fair to a group on average and being fair to an individual. So in fact, just like there's gerrymandering maps for political voting, people have argued that if you make these fair approaches, that you actually get gerrymandering sections of how we're making decisions on people, which is this really interesting allegory, right? So we may be still mistreating people, even if we're treating a group okay overall. There's, of course, the kind of other point of this, which is that we can consider fairness and interpretability together, right? So we can try to force algorithms to be fair and also explain what they're doing in some way. And this is one way we can go about trying to make these algorithms. So one of the point of the series is that we leave a lot of time for discussion. So I was only asked to talk for about half an hour. So I'm just going to kind of wrap up with a few comments here. So one is that I believe explainable AI is necessary for high stakes applications. And to explain why I care so much about that, right? If you look at this, right, we can argue about whether this is an appropriate tool to use for recidivism or not. But the reason we're able to so easily articulate whether this is an appropriate tool to use for society or not is that we can understand what's going on. By knowing exactly how an algorithm is making a decision and forcing it to explain itself, we can actually have these discussions. Should we be using this information? Should we not be using this information? The other thing I want to point is that this is also getting a lot of attention from governments and government regulators. This has been in the news a lot over the past few years in the US as people are complaining about actions taken by social media companies, but also the EU, so the European Union has actually constructed a law called the General Data Protection Regulation, just colloquially known as the GDPR. So if you ever heard people talk about the GDPR, this is all about data and data protection. So they actually have a section on automated individual decision-making, including profile. And it explicitly states that decisions shall not be based on special categories of personal data. So if you're making decisions that are kind of important to an individual, you are going to be, in some sense, held to this law, which you need to actually show that you're not using special categories of personal data. Now, this is still kind of a work in progress, right? It's not actually super clear to me how exactly this gets enforced, who gets to choose what this means or not, but this is something that these government regulators are actually moving forward with. So before we go into the discussion and the Q&A part, I wanted to talk a little bit about our machine learning winter school. So through the Duke Plus Data Science Initiative, we run a lot of programs for the students at Duke, but we occasionally run machine learning schools that are actually open to the general public for a small nominal fee that really just covers mostly cost for the TAs actually, so that you have people to help you work through things. So if people are interested in learning more about the algorithms behind this and the machine learning, we run a 3-day intensive school where we're going to be talking about computer vision in early January. The link is here, and I believe that the organizers are going to send it out to everyone afterwards, but they're usually very well run. The registration opened yesterday, I believe, and if you are interested, I do highly recommend signing up early because they have sold out every single time we have run them, and this will be about our 12th one, something in that order. So I want to leave you, while we start talking about the discussion, I want to leave you with this picture here. So one of the things that's really fun is that not only can AI algorithms actually kind of develop a lot of these kind of interesting societal problems, you can also use them for very fun things. So I will tell you, one of these pictures is a picture of my cat from one of my old cell phones. So this is a kind of an old picture before the phones got really good. And one of these pictures is a computer generated cat, which is developed by something called a generative adversarial network. So one of these cats is a fake cat generated by an AI algorithm, and one of these is my cat's. So while I start looking at these questions that people are asking, you're free to just try to figure out which cat is actually real. All right, so there's a great question in here. So how should organizations go about exposing sort of a logic modeling approach for some of the proprietary algorithms? Should customers be able to choose the level of explainability they would like to see in the products they use? These are really two questions. So the first part is, well, how should organizations actually do this? And this is actually a problem that's pretty tricky to answer. So if you come up with a very simple algorithm that gives your data product, and then you release it to the public, they don't need to pay for your algorithm anymore. So for a lot of these companies, they are actually disincentivized to explain how their algorithms are actually working, because it is treated as intellectual property to know exactly what their algorithm is doing. So if you put out a simple logic model that does just as well as your product, people are just going to use that simple logic algorithm. That is a problem that I don't know how to solve, to be completely honest, because there's these competing kind of problems here, which is that companies do need to maintain their IP. They need to be able to maintain their IP in order to continue making a profit. But we do want to be able to understand what information they're actually using to make a decision. There is a second point here. Should customers be able to choose the level of explainability they like to see in the products they use? My hope is yes, and largely this is customers get to do this a little bit now by choosing to use products that are more explainable, but there aren't that many other products in the public right now. And so companies have tried to make some efforts to try to explain what their algorithms are doing. So for example, Google several years ago now actually released a little tool where it could see what it was guessing about you and your interests. And so I believe you can still find this. And so I search for lots of random things because I'm an academic and we have to look for lots of random links in all these scientific articles and stuff like that. So I discovered that when I was in the middle of grad school, that it thought I was a 40-year-old woman. And that's how it was choosing to make its recommendations for me based on ads, which I thought was curious. But there is some effort to actually go through and try to explain what they're doing to customers, because I think companies are realizing that they need to have a trustworthy relationship with consumers. All right, let me see. There's a question of, can I explain why facial recognition is less accurate for some racial groups than others? So this is a big thing that's come up a lot recently. So the primary reason that there's differing abilities of facial recognition between different racial groups is in training data. So I was going through that example of machine learning in the beginning. So when we were looking at this example where we were giving an example of a mite, and then we say, oh, you should have predicted mite. Here's how you do it a little bit better. A lot of those examples are just whatever we can collect. So for most of the facial recognition systems, they're kind of trained on whatever data you have available. So you use corpus of information on who you have in your data. And so in most facial recognition systems, if not all, they're going to have primarily pictures of people that are white because they're the plurality in the country or the majority in the country. And so because of this, there's a lot more examples of people that are white in these facial recognition systems. And because there's a lot more data examples of this, these systems learn how to better discriminate in that case than for groups of people where you have a lot less data. So there are some efforts that are going on right now to try to increase representation in the data to try to address these problems. And there's a question of, is facial recognition something that should be more regulated given its possible abuse by governments and organizations? So I can only speak about my personal belief here. Yes, it's actually kind of frightening how facial recognition can be used. And it's unclear how it's even being used right now. It's unclear who's using it. We don't know. A lot of police companies are using it. Is it accurate enough to use? Right, facial recognition systems, if you have 100 people, they're remarkably accurate. You can tell the difference between 100 people. But now if we start using on the scale of the US, well, if we're trying to tell the difference between 300 million people, It's a whole lot harder problem. And there are a number of people across the country that look like me. So when you're starting to talk about these very large scale applications of facial recognition, how much can you really rely on them? And this is something that's coming up a lot when people talk about criminal justice. So there's a question about, there's a couple of questions about recidivism, how's it defined? There's a historical corpus where they actually track people that, whether they committed crimes again in the future or were arrested again in the future, I should say. So they're trying to get that accuracy as high as possible. There's a question of, doesn't white balancing of cameras even play a role for the quality of photos or streaming of darker faces? Potentially, I don't really know. There's a lot of debate about what's actually causing these things. There's a question of, what are your thoughts on the impact of introducing more diversity in developers/data science to improve fairness, accuracy, and AI ML? I think that that is a very good goal to go after. There's a quote that I often use from Wired magazine, which is that approximately 12% of AI developers are women, and it's currently reshaping society. People believe that machine learning and AI is reshaping society, and it's very male dominated, and there's very little diversity. And this really is starting to frighten people as it's getting more and more prevalent. So there are efforts to do this, and I don't know how well they're going, to be honest. So I should talk about which cat is real, because actually a lot of people there were lots of guesses on both sides. So the cat on the left is my cat. I'm cheating a little. Yes, congratulations to everyone that said left.
Yes.
Yeah. So the cat on the right is from a website called These Cats Do Not Exist. This is generated from something called a deep convolutional generative adversarial network, which, if you want to know how that works, you can sign up to listen to me talk more in January. I'm going to stop this share here so I can get bigger. Yes, I should say, I picked these pictures kind of intentionally. So the picture on the left is from an old iPhone. I think it's like 7. And there are a lot more image artifacts in the older iPhone because they were trying to do a lot of corrections. So you can see a little bit of kind of weirdness in the image. And it's really because the old image processing algorithms on the real photos were not nearly as good as they are today. So there's a question here. Most AI is designed by engineers, mathematicians, and the like. Is the skill set the best for deciding accuracy, fairness of AI, or do we need to kind of convert philosophers, lawyers, and the like? So we need to actually talk about a lot of these problems as a society, right? There are things that I can do by myself, which is really making these algorithms better and faster, and improving performance metrics and trying to use them, make them use less data. When we talk about how they should be used in society, it really is a lot of people doing it. So at Duke, we actually have people talking about the philosophy of AI. We have people talking about the law of AI. And I believe that, I don't know if Jo is still here, but she can probably tell you, I believe that actually upcoming sessions talk about this a little bit more. And actually bring in experts from law and philosophy to talk about some of these challenges. So there's a question of, can you address the potential for medical image analysis, such as CT and MRI scans? Oh, yes, do you want to?
Dude, yeah, we all have 2 more sessions coming up that we're going to dive a little bit deeper on specific uses of AI and bias related to use in those spaces, and as well as a session that's going to discuss more plainly the responsibilities, capabilities, and liabilities of AI uses in spaces such as medicine and national intelligence and consumer sciences.
Thanks. There's a question about the potential for medical image analysis such as CT and MRI scans. And I want to say I think there's a huge potential for using image analysis through machine learning, and that's actually been an area of research for a long time now. People have talked about computer-aided diagnosis for 30, 40 years now. So one of the things that I wanted to kind of point out, and it's very related to this session, is one of the ways that I'm very excited about doing image analysis for the medical kind of application. So we're talking about CT scans, can you identify a tumor, is actually the explainability. If you just say, if you have an AI algorithm and it just says, hey, there's a tumor in the scan, well, that's hard to integrate into the medical workflow. So you can use it to check, does the doctor and the AI agree, right? If they both say yes, that gives you some information. If they both say no, that gives you some information. But if they disagree, you want to have some way of resolving that. One way of resolving that is to bring in another doctor. But now imagine you have the AI system and it says, well, this is a tumor right here. We think it's right here. And we can actually try to describe, why do we think this is a tumor, right? So for example, and in fact, I know my colleague Cynthia Rudin is actually working on trying to do that. I forget which type of cancer right now. On one type of cancer, they're actually trying to look at tumors and actually trying to get these AI algorithms to both detect tumors, but also describe how they're doing, how they're detecting it and why they're detecting it. And the idea being that if you have this close relationship, you can actually provide this information to the doctor. So rather than trying to compete with the AI, we can have AI-assisted doctors and actually try to improve medicine in that way so that they can make quicker and better decisions than has been happening in the past. So there's a question here, what do you see as the main avenues for bringing explainability, interpretability into national, international standards for AI R&D? That's a really fantastic question. So there was a belief before GDPR came out, that's the General Data Protection Regulation, that it would really increase the kind of the research and efforts on explainable AI to try to get them to explain these algorithms more. And it's happened a little bit, but not nearly as much as you would expect. And so when we're talking about these national and international standards, there really are not many national and international standards. You know, we don't really have them. Then the kind of the EU standard is a standard, but it's only being enforced so much. And I think it's hard to actually understand exactly what it means, even for experts. Maybe the lawyers will tell you differently when they come to talk to you, but to me, as an engineer, I really don't. I know that they want you to be able to explain it and they want you to show that you're not using these categories, but it's actually very difficult. So there's an example of this. This is a historical example in insurance rates that was kind of claimed, right? So you can set insurance rates by zip code. And there's been this complaint that, you know, well, if we set them by zip code, we are somehow allowing them to use kind of different variations in ethnic diversity indirectly, because zip code is highly related to ethnicity. So there's been a lot of debate of, well, is that appropriate information to use? Can we use where someone lives, right? Because that's a surrogate for a lot of other information we know about a person. It's a surrogate for ethnicity. It's a surrogate for socioeconomic status. How much information can we use about where someone lives? But if you're not allowed to use ethnicity, can you use where someone lives, right? It's a really kind of challenging question, and I don't really have the answer for it. There's a question here. Are there recognized technical standards for whether an algorithm is sufficiently explained? No, there are not, right? So one of the things that's happening is that, what does it really mean to be explainable? And I'm giving you some general ideas here, but a lot of what it turns into is kind of this historical example, or sorry, not this quote from Jazz, right? You know it when you see it, right? Like, so if you see it and if it's explained well enough, you know it, and that's explainable AI. And so we don't actually agree as a field. And part of the challenge is what I was mentioning at the end. I claim very proudly that my applications in neuroscience are explainable AI, but they are not interpretable to anyone that's outside of this pretty niche field, right? We are working in this area, and it's a lot of network neuroscience. And if you're outside that area, my results mean nothing to you. So it's very hard for people to actually evaluate, is something explainable or not, because so much of this is field dependent. And there are an awful lot of debates going on about what does it mean to explain a decision from a CNN. And so these things are really large areas of active research. There's a lot of debate on what's going on here. It's a lot of just, well, what's considered explainable from a societal point of view? How close does your explanation have to be? One of the most common ways of actually explaining an AI algorithm is to develop a second, simpler algorithm that makes worse predictions. And you say, hey, here's a simpler algorithm that makes worse predictions, but it makes, because it's a lot simpler, I can explain this simpler algorithm. But does that really explain it, right? Because if your first algorithm that you're really using to make decisions doesn't agree, how do you explain those discrepancies? And so I'm going to probably stop here before I go off on a very long rant about all the different ways we can do this, but it is not agreed upon. These are things that are actively debated in the field.
I've got one final question for you. So when we think moving forward into the future of AI and what's next on the horizon when it comes to this explainability piece and where we're headed, where do you feel like that's going? Where are we headed in that space? And what are we doing here at Duke to make sure that we're on top of that research?
So that's a great question. There are several labs at Duke that are very interested in the algorithmic part of explainable AI. My own research group has some of this. Cynthia Rudin has a lot of this. There's a number of other, Guillermo Shapiro, but we also are exploring it from kind of the broader societal impact, right? So we have people that look about what are the impacts of AI on society. We have people talking about the philosophy of AI. We have people talking about the law of AI. These people, we largely talk to all of these people. We talk to each other constantly. Well, maybe not constantly, but yeah, it's a little bit surprising because when I got hired as an engineering professor, I was not expecting to start talking to people in philosophy and people in law who are very interested in the things that we're working on. And so as far as what's next for this is that, what's happening in a lot of these fields in machine learning is that it's becoming more apparent to develop standards. And one of the actual very surprising things is that one of the arguments is that we should push for more human evaluation of algorithms. So there's a lot of arguments that, well, if we're claiming something's explainable, the only way to do this is to take 30 people, not tell them whose algorithm is used, and ask them to judge whether they understand the decision, whether they really think it's explainable or not. And that's a kind of a interesting take from such a field that is so numerically defined, that was so metric defined, to say, well, now our metric is going to be human evaluation. And so that's a really interesting kind of point of view. And obviously that's not the only one. But yeah, I can keep going, but I think that's probably good.
Thank you so much for everything today. I know I'm novice about this area of research, and I really appreciate you taking some things and breaking them down, making them much simpler for us. And thank you to our audience for coming on. For many of you, this is your lunch hour. For some of you who are joining us from other spaces, thank you for taking time out of your day to be here and learning more about the black box with us. So I populated it in the chat already, but our next session is November 17, and we are looking at Behind the Machine with algorithms, AI, and bias. And that's going to be a panel discussion with representatives from the law school, Fuqua, Pratt, and Stanford School of Public Policy. And then also I wanted to give you all a real quick resource. We actually have a living syllabus that includes different videos, events, articles, podcasts, all about what's happening at Duke in the AI space. And so feel free to check that out. It's got a multitude of resources. Some things written by David, and then his colleague Cynthia is also represented in there. But We look forward to having all of you back at the Forever Learning Institute with us soon, and we hope that you have a wonderful rest of your day. Thank you so much.